recording on this computer, and I will share my desktop. Let's get after it. So before I start with the problems from the worksheet, I don't think the worksheet is uploaded yet, so I'll upload it later on today. I just want to go over the logarithmic differentiation one more time, just so that it kind of it's more clear as to why we use it. So we covered implicit differentiation, which is differentiation using our differentiation rules. We covered the chain rule, which allowed us to deal with what I call nested functions, and it's something like sine of, in the bracket, 3x squared plus 2 is our function, and we need to find d over dx of that. So the chain rule helped us with this. While we were learning the implicit differentiation, we learned the product and the quotient rules, which allowed us to deal with fractions and products of functions. But I guess we hit the wall at some stage, and an example of a function where we hit a wall is something like this: 1 plus x by x minus 3. Let's see how that's squared. All that divided by x square root of x minus 1. That's just a random function. And the reason why we hit the wall over here is because in this particular case, what we are dealing with is in the numerator, we have a product of two functions. In the denominator, we have a product of two functions. And between the numerator and the denominator, we have a quotient. So we have two applications of the product rule and the quotient rule that we would have to use in order to be able to differentiate this function. And it is doable, but it's a pain. And I would say it would be unwieldy if the functions that we would deal with in here became more important. So to the rescue comes this very interesting fact. So if we have to take a derivative of natural log of some function x minus, let's say, x squared minus 3, we're taking a derivative of this particular function. And in more general terms, I want you to notice that this can be called y, that this is a function where y is equal to x squared minus 3. So if I take a derivative of this particular expression, what I'm ending up with is, by the chain rule, I take a derivative of what's in the log, which would be 2x, and I multiply it by a derivative of the natural log, which is essentially 1 over whatever is in the logarithm. So that would turn into 2x over x squared minus 3. And the fact I want to point you towards is that the expression over here is the same as expression that I said is equal to y, which is my inner function, so to speak. So in more general terms, we can say that if we take a derivative d over dx of natural log of some function, d dx of natural log of some function, the expression we end up with is 1 divided by the function multiplied. Above the line in here, we have a derivative of whatever was in the natural log. So we have 1 over y multiplied by the derivative of the function of y. So dy dx. dy dx is the derivative of whatever is in the natural log. 1 over y is essentially this expression. So okay, so this is the kind of step that we're going to take, because if we want to find the derivative of some very complex function, what I can do is just transpose this expression and get that dy dx is the same as y, which is the function, multiplied by d over dx ln of y. What this tells me is that if I take a natural log of the function, my function being this expression denoted by y, and then take a derivative of that natural log, and then multiply that derivative of the log by the function, what I'm ending up with is the derivative of the original function. And it turns out that this particular way of dealing with functions is super useful for expressions like the one over here. And also another family of expressions where we have something like 2x to the power of x, or 2x e to the power 2x, wherever we deal with function of x, and x is present both in the base of the power as well as the exponent. So to simplify it a little bit, logarithmic differentiation is useful for complex and difficult functions. So if I was to apply this particular set of solutions or the way of solving to my original function, let me just get rid of this. The first thing I would do is I would take the natural log of this. So by the law of logarithms, I have a product above the line, a product below the line, and I have a division between numerator and the denominator. So ln, natural log of 1 plus x multiplied by x minus 3 squared divided by x by root x minus 1. We can rewrite this as natural log of, let me just maybe do it in steps, 1 plus x by x minus 3 squared, and then minus natural log of x root x minus 1. So this is kind of following the laws of logarithms that we had learned before, before we ended up because of COVID. So continuing with this, now I can start expanding. So I'm going to expand in the first logarithm. That will turn into ln of 1 plus x. And that is what I'm adding to it then is, because this is a product, so by law of logarithms, product of two logarithms turns into an addition. So a product of two functions in a logarithm turns into an addition of logarithms, plus ln of x minus 3 all dot squared, and then minus, I'll say, put the bracket over here, ln of x plus ln of root of x minus 1. Bear with me for a second. I just need to do a mute over here. So continuing with simplification of this, I'm going to end up with ln of 1 plus x. This is the first expression, plus power drops in front of the logarithm to ln x minus 3 minus ln of x, and then plus, this is going to turn into a half because root is a power of a half, minus half ln of x minus 1. So then what I'm going to do is I'm going to take derivative of all this. So that's d dx of this particular expression is equal to, from the first bracket, that's simply 1 over 1 plus x. So that's derivative of whatever is inside in the function, which is simply 1, the coefficient in front of x, and that's divided 1 over y by dy dx, and y is the expression, the logarithm. So y equals to 1 plus x, derivative of 1 plus x is 1, and that's divided by 1 plus x, plus 2 divided by x minus 3 minus 1 over x, and then finally minus, and that actually should be minus 1 over here. Minus 1 over x minus 1 over 2x minus 1. So this is the derivative of this particular logarithmic expression. And to get dy dx, which is the derivative of my original nasty looking function, the derivative of this function over here, all I need to do is just multiply this logarithmic expression by the function by 1 plus x minus 3 over squared, all that over x root x minus 1. And we can leave it here. This long expression is a resulting derivative of this expression over here. And sorry about the messy writing, it will clear up in a little bit. Now, again, I want to just stress this one more time, that logarithmic differentiation helps us in finding derivatives of functions that are difficult to deal with. And I have a number of examples. So before I start into the differentiation, I just want to maybe do 2 or 3 examples on how to deal with derivatives of logarithms. So the first one is actually, I think I have that uploaded to Moodle. I forgot whether I did it yesterday, but I think I actually did this, so that should be, you should be able to look at this today as well. So let's take a look at problem number 1, which is just very simple, 4x minus 10. Then let's take a look at number 3 and number 8 and number 9. So we'll do 4 of them. So number 1, y is equal to, bear with me for a second. So y is equal to ln of 4x and minus 10. So that's all well and good. Now I need to find dy dx, and that's d over dx of ln of 4x minus 10. So this is a compound function. I have an inner function 4x minus 10 and the outer function natural log of whatever is the inner one. So I'm using chain rule, and by chain rule we have derivative of the first one, the inner one, times the derivative of the outer one. So that will be 1 over 4x minus 10 multiplied by 4, and that's simply 4 over 4x minus 10. And taking a look at the third one, slightly more complicated version of the same example. So y is equal to 3x cubed, sorry, natural log of 3x cubed plus x dy dx. So again, taking derivative of the inner function, that's 3 by 3, which is 9x squared. Derivative of x is plus 1. And below the line, we just rewrite whatever is in the natural log, which is 3x cubed plus x. And that should suffice for this particular example. Taking a look at another function, we're going to do number 8, which is 2 natural log of sine x. So let me clear this. Y is equal to 2 ln of sine of x. Just as a reminder, derivative of sine of x is cos x. So to get the derivative of this, y is equal to 2 d dx of ln sine x. Note that I took the constant out of the derivative because that's something that I can do. Constant doesn't really have that much impact on what the derivative result will be. It's just a coefficient for the resulting function. So if I take a derivative of this, I'm going to end up with derivative of sine of x is cos x. And we divide cos x by what's in the natural log, which is sine x. And that's cotangent of x. And actually, let me just remember about that coefficient. So that should be 2 cos x divided by sin x, which is 2 cotangent of x. And for the last example on just this side, let me do number 9, which is again just slightly more complicated derivative of involving more terms, but again the principle is very, very similar. So y is equal to natural log of 4x cubed minus 6x squared plus 3x, and that's that. So dy dx, I'm going to take a derivative of whatever is inside in the bracket. So then 3 by 4 is 12x squared. 2 by 6 is 12. And then plus 3. And below the line, I'm just going to repeat whatever is in the bracket. So that's 4x squared minus x cubed actually here. No, x squared, that's right. 4x cubed minus 6x squared plus 3x. And that would be the resulting derivative. Perhaps there is some way of tidying it up a little bit. Maybe there are coefficients that we can take out, but I don't see it immediately. So we can just leave it as is. Okay, so the whole idea for the first part of this exercise was to gently introduce us to the second one. So we're going to do the 6 problems from this exercise over here. So let me just clear this. In problems 1 to 6, we're going to use logarithmic differentiation to differentiate the given functions with respect to the variable. And in this case, it's very straightforward because a variable is x in all examples, except for, function number 5, where we have 3 theta sine theta cos theta. Okay, so let's get into it. Again, and the steps I'm going to follow is as follows. The first step is I'm going to take, I'm not going to rewrite the function. What I'm going to do is I'm just going to rewrite it after I take the natural log. So taking natural log will be the first step I take. Once I take the natural log of the function, then I'm going to differentiate the natural log. And once I differentiate the natural log, I have essentially arrived at the derivative, because to get the derivative, I just need to multiply the resulting differential by the original function. So for the first example, we have y equals to x minus 2, x plus 1, and all that over x minus 1 by x plus 3. So taking the derivative of this, natural log rather, ln equals to natural log of x minus 2 plus natural log again of x plus 1 minus, because that's below the line, ln of x minus 1, and minus again. There is a plus between those two. When you take natural log of this product, it's a plus, but because it's below the line for the resulting expression, it's going to be minus. So minus ln of x plus 3. So then onto derivatives, dx ln y equals to, the first one is 1 over x minus 2 plus 1 over x plus 1 minus 1 over x minus 1 and minus 1 over x plus 3. And this particular expression is the same as 1 over y by dy dx. So to get dy dx, all I need to do is just multiply this expression, so this part over here, by y, which is this function here. So that is, again, x minus 2, x plus 1 over x minus 1, x plus 3, multiplied by 1 minus x over 2, 1 over x minus 2 rather, plus 1 over x plus 1, minus 1 over x minus 1, and then minus 1 over x plus 3. And that's it, that'll do. We possibly could try to simplify it a little bit, but that would end up with a horrendous fraction with a really nasty denominator, like just unnecessary algebra. We can leave this expression as it is. No need to simplify it any further. So this particular expression is the expression for the derivative of this function over here. And we can continue in the same manner. So the next one, we're dealing with x plus 1. So that's my y equals to x plus 1, 2x plus 1 cubed, all that divided by x minus 3 squared, and x plus 2 to the power of 4. So then taking natural log of this, same approach, and I suppose the only difference between the previous problem is that now we have powers and indices and powers, and we just need to be careful that we apply laws of logarithms while dealing with those terms. So ln of y equals to ln of x plus 1. Product between those two logarithms, so that's a plus. And then remember that whenever you're taking a log of a term that's in a power, the power number drops in front of the log. So that will turn into 3 ln of 2x plus 1. And then minus 2 ln of x minus 3. And then minus again for ln of x plus 2. So that's the ln of y. Now, next step is to take d dx of ln of y, which is equal to, from the first bracket, that's 1 over x plus 1. From the second bracket, that would be plus 3 over 2x plus 1. From the third one, minus 2 over x minus 3. And from the fourth term is minus 4 over x plus 2. So that's the ddx of natural log of y. And again, I remember that this expression has the value of 1 over y multiplied by the derivative of the function, dy dx. So from here, I'm getting that dy dx equals to, again, multiplying by the whole function, so x plus 1, 2x plus 1 cubed, divided by x minus 3, all that squared, x plus 2 to the power of 4, multiplied by all of this, 1 over x plus 1, plus 3 over 2x plus 1, minus 2 over x minus 3, and then finally minus 4 over x plus 2. And that's the derivative. Again, little expression which is a little complicated. And that's that. So that's that, that's that. Okay, so let's take a look at another expression. Again, expression number 3 follows the same vein, except this time to make our life a little bit more exciting in these derivatives, we have to take a derivative of a function containing a square root. So y equals to, let me just close this here. So we have 2x minus 1 above the line multiplied by, instead of writing square root of x plus 2, what I'm going to write down is x plus 2 to the power of half. So now, rather than having a square root, I have a power. and I can take a natural log of this expression easy now. And below the line, we'll have x minus 3 multiplied by, and whenever I'm dealing with a square root of an expression that's a power, the fraction that denotes that there is a root takes such form that the number in the denominator of the fraction tells me the power of the expression under the square root, and then the numerator of the fraction tells me that degree or the order of the root. So this is a square root, which tells me that x plus 1 has to be to the power of 3 over 2. 3 from under the root, 2 from the order of the root. So now to take the natural log of y, we get natural log of 2x minus 1 plus half of x plus 2, half of natural log rather. And then minus natural log of x minus 3, and last but not least minus 3 over 2 natural log of x plus 1. So next step is to take a derivative of this, d over dx ln of y, and we're going to end up with 2 divided by 2x minus 1, and then plus 1 over 2 bracket x plus 2.
Sorry, I have questions. Why 2 divided by 2x minus 1?
Good question. And what I will point you towards is the fact that when I'm taking derivative of ln of 2x minus 1, this is going to be d over dx of 2x minus 1, so the derivative of the inner function, multiplied by 1 over 2x minus 1, from the fact that this is a derivative of the natural log. So the 2 above the line comes from this derivative over here. In other words, to explain it, I can say that I'm dealing with function y, which is equal to natural log of u, and u, which is equal to 2x minus 1. And by chain rule, dy dx equals to dy du multiplied by du dx. So dy du is just the derivative of natural log, which is always 1 over the function or the expression in the logarithm. So that will be 1 over u, and that's multiplied by du dx. Function u is 2x minus 1. Derivative of this is simply 2. So then we're ending up with 2 over 2x minus 1. Does that sort of answer the question?
Thanks.
Okay. I hope it does. So let me just step back and continue with that derivative. So that's for the first one. The second one, the third one will be minus 1 over x minus 3. Maybe I can change it back to black color. X minus 3, and finally we have minus 3 over 2. So above the line we'll have 3 anyway, and then 2x plus 1. And rather than rewriting it again, I'm just going to say that dy dx equals to this multiplied by the function, which is 2x minus 1 by x plus 2 to the power of half, all that divided by x minus 3, and then again x plus 1 to the power of half. That's number 3 done. So number 4 starts into introducing some more interesting functions. So let's get right after it. So we have that y equals to e to the power 2x multiplied by cos 3x, all that divided by root x minus 4. So again, the first step is to take natural log of everything, and of y equals to natural log of e to the power 2x is simply 2x plus ln of cos of 3x, and then minus ln of x minus 4 to the power of half. So I'm just going to put half in front of natural log. So then the next step is to take dy dx, dlny rather. So derivative of 2x is 2. Derivative of natural log of cos 3x. So first step is we have to take derivative of cos 3x. And just looking into my handout, derivative of cos 3x is minus sine of x. So that will turn into minus 3 sine 3x. The reason why there is a 3 in front of sine 3x is that again, it's a compound function. So I have an inner function, 3x, and the outer function cos of the inner function. So the derivative of the inner function is 3. Derivative of the outer function is minus sine. And below the line, from the derivative of the natural log, we get cos 3x, and then minus 1 over 2 in the bracket x minus 4. There's a way I can simplify it just a little bit, so that will turn into 2 minus 3 tan 3x. Sine over cos of the same angle is equal to tan of that angle, and that minus 1 over 2x minus 4. And then to get the final function dy dx, again we have to multiply it by the original function, which is e to 2x cos 3x divided by root x minus 4. Okay, so that's that one done. Number 4 and number 5, we have sine 3 theta, rather y equals to 3 theta sine theta cos theta. So let's get right into it. So clear this and clear this. So we have d over, y equals to ln of, it's 3 theta sine theta and cos theta. So then take a natural log of both sides, and I have, I'm going to keep this together. This is 1 and this is 1, so that will be ln of 3 theta plus ln of sine theta plus ln of cos theta. I'm taking derivative of everything, so the dx of this expression, we're going to end up with 3 divided by 3 theta, so 3's will cancel. Again, derivative of sine is cos, derivative of cos is minus sine. So plus cos theta over sine theta, and then minus sine theta over cos theta. To simplify it a little bit, we can end up with 1 over theta plus cotangent of theta and minus tan of theta. And to get the derivative of the original expression, dy dx, we just need to take this and multiply it by our original function, which is 3 theta sine theta cos theta. And maybe you can try to simplify it a little bit further, but I think this is sufficient. Okay. So these are the kind of compound functions that we would normally have to deal with, but actually we have another one. So that's the last one is very nice because we're dealing with natural log as well. So y is equal to 2x to the power of 4 tan of x divided by e to the power of 2x, and that multiplied by ln 2x. So natural log of this will be equal to 4 ln of 2x for natural log of 2x plus ln of ln of tan of x, and then minus 2x, and finally minus ln of 2x. Okay, so take a derivative of this, dx ln of y. So from the first one, inner function is 2x, so that's 4 multiplied by 2 over 2x. So 2's will cancel, and we're going to end up with 4 over x. From the second one, we have derivative of tan is, if I remember correctly, second squared. Yeah, that's second squared, plus second squared divided by second squared of x divided by tan of x, and then minus derivative of 2x is 2. And this is an interesting one. So for the upper function, I have to take this is my outer function. My outer function is, let me maybe do it over here. So I have d over dx ln of ln 2x. So y equals to ln of u equals to ln of v, and v equals to 2x. So we can see that this is a sort of a triple whammy. So dy dx equals to d y du multiplied by du dv and multiplied by dv dx. So dy du is 1 over u. Du dv is 1 over v multiplied by 1 over v, and dv dx is simply 2 multiplied by 2, and that will turn into 2 multiplied 1 over u. So my function u is equal to ln of v, so 2 multiplied by 1 over v 2x ln 2x. So function v is 2x and function u is natural log of 2x, and that will cancel. So we're ending up with minus 1 over x ln of x. So that's that done then. And there is one simplification that we can actually do in this expression, because secant squared x over tan x, if I look over my trigonometric identities, where is it? Secant is 1 over cos squared. Okay, so I can say that secant squared is 1 over cos squared of x. And if that's the case, I can do that substitution in here, and I can substitute sine over cos for tan of x. So sec squared x divided by tan of x is the same as 1 divided by cos squared x by sine x over cos of x. And that will simply cancel. So we're ending up with 1 over sine x cos x. So again, I can replace secant squared x by this expression, which is what I'm going to do. And I'll also tidy this a little bit. So that's 4 over x and plus 1 over sine x cos x, and then minus 2 ln x. So that's dx d natural log of y, and to get to dy dx, we just need to multiply it by original function, which is 2x to the power of 4 tan of x all over e to the power of 2x and natural log of 2x. For me, being able to differentiate this function is, is quite powerful, because if we were to differentiate this using the standard approach with product and quotient rules, it would be well, it wouldn't be nice thing to do, let's say. So let me clear this and move on to question number 3. So we have 4 problems where we need to differentiate. Then we need to do we need to show something related to our derivatives, and then do some evaluations. So what I'm going to do, I'm just going to go over the first 4 examples, excuse me, and that will be it for today. You should be able to complete the remaining to yourselves. So let's get right into it again. So for the first question, we have to take a derivative of function y equals to x to the power of 2x. And again, because this is a sort of a compound function where we have the variable in the base of the power and the exponent, we don't actually have a method for dealing with this type of function in our standard toolkit. There is no substitution that we can make, or anything that we could apply to use any of the known rules, which means that we actually, for functions which contain the variable both in the base and the exponent, we have to use the logarithmic differentiation. No other way to do it. So take log of both sides, ln y equals to ln of x to 2x, and that will turn into 2x ln of x. So we have what you can notice over here is that we have a product of 2 functions, 2x multiplied by ln x. So we have to apply the product rule. So product rule. So to get the differential, rather dx ln of y. Product rule tells me that I have to take a derivative of the first one, 2x multiplied by the second one, and then add to it derivative of the second one multiplied by the first one. So derivative of 2x is simply 2, and derivative plus 2x, and derivative of ln x is 1 over x. So I can simplify this a little bit. X's will cancel, and that is equal to 2 ln x plus 2. And that's the expression for the ddx of ln y. Now, it still doesn't tell me what the derivative of the original function is, but I know that this is equal to 1 over original function multiplied by derivative of the original function. So from here, dy dx is going to be equal to 2 ln of x plus 2, all that multiplied by x to the power of 2x. And that's the job done. For the next one, let me just clear this. So for the next one, I have y equals to 2x minus 1, all that to the power of x. And taking natural log of both sides, ln y rather, we're ending up with ln of 2x minus 1 to the power of x, which is going to turn into x, ln of 2x minus 1. And now I can start taking the derivatives. And again, we're dealing with a product over here, so we have to apply product rule. So d ln y dx is equal to derivative of x multiplied by ln of 2x minus 1, and then add to it x multiplied by ln of 2x minus 1, and take a derivative of this. So doing this, we're ending up from the first expression, that's just ln of 2x minus 1, plus x multiplied by derivative of ln 2x minus 1. So that will be multiplied by above the line by 2, and below the line we're ending up with 2x minus 1. So that's d ln y dx, and to get dy dx, all I need to do is to take this expression and multiply it by 2x minus 1 to the power of x. Just bear with me a second and make sure that I have this one right. Yeah. So we can rewrite this as 2x, but that's all the same. So for the next one, what I'm noting is that this is a derivative of a root-like expression, I guess. So y is equal to root of the order of x plus 3. Not too difficult. But that will turn into x plus 3 to the power 1 over x. Okay, so that's a slightly different expression than what we've dealt with. Now, taking natural log of both sides, we're ending up with 1 over x natural log of x plus 3, or I can rewrite it as natural log of x plus 3 all over x. So now to take that derivative, dx of ln y, I'm taking derivative of this expression, which is ln of x plus 3 over x. But what I'm pointing you towards over here is that this is a fraction, and the fraction tells me that I have to apply the quotient rule. And if I'm applying quotient rule, what I'm going to do is take the derivative of the, let me just zoom in over here so the quotient rule is more apparent. So we have derivative of f in the numerator and g in the denominator. So we're multiplying derivative of the numerator by the denominator minus numerator by the derivative of the denominator, and all that over denominator squared. So for us, that's going to be above the line we have f of x, so which is x multiplied by derivative of ln of x plus 3 minus ln of x plus 3 by the derivative of x, and then all that has to be over x squared. So if I take that derivative, what I'm going to end up with for the first one is x divided by x plus 3, and then minus ln of x plus 3 multiplied by 1, and all that has to be over x squared. And there is a little simplification that I can do for this one. So if I rewrite them both as separate fractions, this will turn into x over x squared x plus 3. This denominator multiplies by x squared, and that's minus ln of x plus 3 but all over x squared. And the square and the x cancels, so that ends up with 1 over x by x plus 3, and then minus ln of x plus 3 by x squared. So that's my derivative of the natural log, and to get the derivative of the original function, I take this expression and multiply it by root x to the order root of x plus 3. And that's it, job done. And the last one is 3x to the power of 4x plus 1. So let's clear this, clear. I think I have something else. Yeah. So we have function y equals to 3x to the power of 4x plus 1. Then natural log of y equals to ln of 3x to the power 4x plus 1. And that will turn into, I'm going to maybe separate it a little bit first. So this actually, I need to rewrite this a little bit. The reason I had to rewrite this because we have a product of 3x, so that's why it's ln 3 plus ln x 4x plus 1, and the power is only applicable to the x. The power doesn't apply to 3x, so that's why I had to rewrite this a little bit. So that bracket is not necessary, the bracket is around x. So simplifying it a little bit further, we're ending up with ln of 3 plus 4x plus 1 ln x. And now that's that done, I can take a derivative dx of ln of y. So derivative of the constant is 0, and then I have to take a derivative of, so that will go into 0, I don't need to worry about it anymore. And then I'm taking derivative of this product, and again it's a product, so derivative of the first one times the second one, so that will be 4 ln x, and then plus derivative of the second one times the first one, so that's 4x plus 1 all over x. So that's the expression. And now that's that done, I can put this into the bracket, just rather than drawing a big line, wipe this off and say that dy dx equals to the derivative of the logarithm multiplied by original function, which is equal to 3x 4x plus 1. And that's that. Okay, so we went through a nice few examples. And then the next bit is that we have to show that when y equals to 2x to the power of x and x is equal to 1, then derivative of equals to 2. So this example actually, really what we need to be concerned about is what's the dx of x to the power of x. So that's something that that you should do. Actually, I might take this derivative and then you can apply it to the proof. So d dx x plus x to the power of x. So taking the natural log of both sides, I'm going to end up with x ln x, and then taking derivative of this is equal to ln x plus x over x, which is obviously 1. So that equals to ln over x plus 1. So derivative of x to the power of x is ln x plus 1, And now, so that's the derivative of the natural log multiplied by x to the power of x. So that's derivative. And then you can apply this derivative to the expression when x equals to 1. Okay, so I'm going to leave this here actually. The remaining two problems I'm going to leave for you. So go back to Zoom. And